And welcome, everyone. This is the SWOT Data Inversion and Assimilation Working Group. And so the intent is to have a pretty informal discussion, but starting with a presentation from Ariane Verdy, who's going to talk about 4D VAR assimilation for the California current system. And then we'll have open discussion. The schedule has been released for the next few months, and we actually have speakers scheduled all the way through June. So lots to keep people engaged. So go ahead, Ariane.
Thank you. Okay, when I tried this earlier, it worked no problem to share my presentation. Now I'm not seeing it. So it's because it's not open. Okay, give me a second. Sorry about that. There we go. Okay, does that look right?
Yeah, that looks good.
Perfect. Okay. Um, well, good morning to those in the US. Good evening to the people in Europe. So I'm Ariane. I'm very lucky to be working with Sarah and Matt and Bruce and Ganesh. Sorry, that was my cat stepping on my keyboard. Okay. Um, so I'm going to present work from a manuscript that is currently in revision. So any feedback is very much appreciated. And I'll try to give a brief presentation so that we have plenty of time for discussion afterwards. Okay, so we're doing 4D VAR assimilation. And for people who are familiar with the ECHO products, we use the same method that they use to make their global state estimates, but we're applying it to a regional setup, in this case of the California current system. And we chose that region because during the SWOT CalVal period, there was a crossover off the California coast. And so we have, this was the 1 day repeat orbit. So we have 2 observations every day in this crossover region. And in addition, there were in situ instruments that were deployed. We have 2 gliders and 11 moorings in that region that give us more data to assimilate. So the setup is the MIT GCM with a 2-kilometer horizontal grid spacing. We have 100 vertical levels and a time step of 5 minutes. And we run the model for a 31-day period in May 2023, so during the CalVal period. And so our assimilation window is this entire 31-day period. So we're building on existing state estimates in the region. So Ganesh and Matt have been doing data assimilation in the California current system for a while. And so we have a setup that's pretty well established. And the observations that are typically assimilated are the along track SSH observations from nadir altimetry, the satellite satellite SST, the in situ profiles of temperature and salinity from Argo, and lots of spray glider lines. These green tracks there are repeat glider observations. So I call this this is referred to as the Global Ocean Observing System, acronym GOOSE. And the way to fit these observations is by adjusting what we call the control variables, which in our case are the atmospheric state. So the winds, the heat fluxes, precipitation, so all the this surface boundary condition, and the initial temperature and salinity 3-dimensional fields. In 4D VAR, we adjust these controls, which are, like the inputs to the model, but we do run over the 31-day period without nudging. So we do get a dynamically consistent state estimate. Um, okay, I'm going a little bit fast over here, but the novel aspect is obviously the assimilation of the SWOT data. So we use the L3 product, and we, as expected, it brings on some challenges, right? So, okay, the first challenge is that the existing data assimilation system in the MIT GCM was not particularly well suited for observations like SWOT, which are very high resolution, but they're also sparse. Um, and so it's a high demand for the system. Without going in much detail, we ended up writing a new piece of code to address that issue. So in 4D var, we have a cost function that's defined as the squared model data misfit scaled up by an uncertainty. And the the way this cost was calculated in the MIT GCM relied on either interpolating the observations onto the model grid or interpolating them onto a fixed set of vertical levels, neither of which works particularly well for the sparse SWOT data set. So our approach has been to kind of think in observation space rather than in model space. And we created a package which is called ObsFit that gives us a lot of flexibility in terms of how the cost function is calculated. So I'm not going to talk much about ObsFit, but it is now part of the MIT GCM. It's an alternative to the existing Echo and Profiles package. It's actually evolved from the Profiles package, but adding more flexibility again. So if there are MIT GCM users, if you want to check it out, try it, that would be great. And again, any questions or feedbacks are appreciated. Okay, so we ended up using ObsFit for the assimilation of the SWOT observations, but the prior constraints that were already in the setup, we just kept the older cost function packages. Okay. Second challenge is that when we start thinking about small scales, submesoscales, we run into issues with the stability of both the forward model and the adjoint model. So the 4D var is an iterative method. And so we run a forward model, we calculate the cost function, then we run the adjoint model, which gives us the sensitivity of this cost function to our control variables. So we have this gradient, how the cost function depends on the model inputs. And when the cost is large, because the misfits between the model and the observation are large, we can run into issues where these gradients get very large and they can even blow up because of instabilities in the adjoint model. So the way that we deal with that is that we increase the viscosity in both the forward and the adjoint, and that damps out the small scales, and it allows us to fit the large scale in our model. And so the large scales are usually the balanced motions. And so we try to fit that first, and we run a few iterations at high viscosity. And then when the misfits are smaller, we're able to lower the viscosity and get the adjoint model to give us, reasonably behaved gradients. So there's no more blowing up. And then we can do a few more iterations and try to fit the smaller scales. So that is the idea. And we ran three experiments. So we produced three different state estimates. The first one assimilates only the SWOT observations. The second one assimilates only the goose data set, so the nadir altimetry, SST, Argo, and spray. And the third one puts everything together. And I should mention that because there's so much SWOT data, we did some subsample it. We took basically every 10-kilometer in both the along track and across um, directions. And, we feel like this is our first try at assimilating this. We don't think we can fit the 2-kilometer scales at this point. So as a first go, we just subsampled everything. And the in situ CalVal data was not assimilated, so that gives us an independent data set we can compare to. Same thing with the high frequency radar data. We have this coastal HF radar data that measures surface currents, and so that is another independent constraint. Okay, this is what the cost looks like as a function of the iteration number. This is for the SWOT only assimilation. So iteration 0, we initialize the model. In our case, we took initial conditions from GLORIES and atmospheric state from ERA 5. And we run, this is our forward model run, iteration 0, and we get a cost that reflects the Wade model observation misfit. And this is run with the higher viscosity of 100. And we do a few iterations, cost goes down a lot, then it starts plateauing a little bit. We reduce the viscosity. This creates more small scales in the model. So those don't necessarily fit the observation. So a little bit of a jump in the cost, but the cost goes back down. It starts decreasing. It goes back about to the same level as it was with the higher viscosity. But more importantly, the adjoint doesn't blow up now. If we had tried the lower, and we did, if we tried to run the adjoint at low viscosity from the get-go, it just doesn't, the cost will not descend because it's not well behaved. And what I'm plotting is the scaled costs because in lower viscosity, there's just more variability. So the absolute cost is a little bit higher at lower viscosity. So I scale it by the variance of SSH along the SWOT tracks, which gives us a measure of, so it's the cost normalized by the variability, which is a more meaningful number than the absolute cost. Okay, these are wave number spectra. So we have the two passes in the domain. So I'm plotting the spectra separately for each pass. The red curve is the SWOT observation. So basically every day we have one pass and I subsampled every 10 kilometers. So I have something like 10 lines along which I'm calculating the spectra. And then I average the spectra for the May 2023 period. So, okay, so this is the average spectra for SWOT data. The gray curve is the spectrum for the forward run, so in iteration 0, before data assimilation. And the black curve is after data assimilation. So this is our state estimate. And this is for the assimilation of SWOT and goose observations. One notable difference is that the forward model is run with the high viscosity, whereas the state estimate is with the lower viscosity, so that's the difference in the energy at small scales. And so in both cases, and I would argue that the fit between the state estimate and the observations is pretty good up to approximately 70 kilometer. So we fit the larger scales well. We are not resolving the submesoscale at this point, but we're moving toward, in the direction of getting the smaller scales fit better. Still work in progress. If I compare with the assimilations where I withhold the goose data set or I withhold the SWOT data set, the fit to the spectrum of SWOT data is not as good. So this plot is a little bit busy, but the gray and black curves are the same as before. The observations are now orange instead of red, but that's the same spectrum. The green curve is the case where I only assimilate SWOT data. And it's interesting that it has skill at some scales, but it's not doing as well as the the state estimate that assimilates goose data set as well. And the blue curve is the assimilation that withheld SWOT data. And again, the skill is not nearly as good. So there is value in both data sets, I guess. This is kind of a summary of how well we fit each data set for each assimilation. The orange symbols are for the independent data. Sorry, opposite. The data that's assimilated. So this is the Argo temperature profiles, then the Argo salinity, spray temperature, salinity, the remote sensing SST, nadir altimetry. Then we have the SWOT constraints, and here are all the independent data sets. So these are the CalVal mooring and glider temperature and salinity. I'm plotting the normalized cost, which is the cost divided by the number of observation in each data set. And so the first bar is our forward model, and then we have the assimilation that only assimilates SWOT. So you can see that so these are the goose data sets. There's usually a little reduction in costs, but assimilating goose obviously makes a much bigger difference. And for the SWOT data set, when it is withheld, again, slight reduction, but when we are assimilating SWOT data, we can bring it down to a normalized cost of 1, which means that we are within the prescribed uncertainty, since the cost is misfit divided by the assigned uncertainty on this data set. And then it's validating to see that these independent data sets also get a reduction in cost. So even though we're not assimilating these data, we fit them better, which is reassuring that our state estimate is consistent with the real ocean. Okay, this is showing the RMS difference between the SWOT data and the model equivalent. So the modeled SSH along the SWOT path. And this is plotted as a function of time, so over the 31 days of our simulation. The gray curve is the forward model run. So we get a slight increase in misfit over the course of the unconstrained run. And then after data assimilation, we have this black curve. And the uncertainty that we've assigned to the SWOT data is 2 centimeter. And that's based on Jinbo's work and papers. And for most of the state estimate, we are within this 2 centimeter uncertainty. Now, there is, I don't know if it's an issue, but there's this kind of anomaly at the beginning where we are not fitting the data as well. And I'll come back to this in a little bit. The Aviso product, if I also compare Aviso along SWOT with the SWOT observations, uh, the value, the fit is approximately the same as ours. But Aviso gives us a two-dimensional SSH product, whereas the state estimate, has this three-dimensional dynamically consistent feature, which it makes it harder to fit a specific data set. So we're kind of pleased with this result that we can, oh, it's a cat again. You still see my screen, I hope. That it's, yeah, that we're fitting as well as Aviso. And so this is same plot, but I've added two curves. And these are runs that I guess withhold some of the controls. So I did a run where I used the optimized initial conditions, and that's the green curve, and just forgetting about the atmosphere state controls. And one where I did the opposite. I turned off the initial condition controls and only used the atmospheric controls, and that's the blue curve. So this gives us a hint of what's happening here at the beginning of the state estimate. So it looks like the initial controls are working toward reducing the misfit on day 0, but their effect only lasts for the first week, really, and then it, gives us a higher error near the end of the simulation. Whereas the atmospheric controls are working against that. And I need to look into more details. This is just kind of a new result for me. And I don't understand exactly what's going on yet, but something in the atmospheric state is causing larger misfits initially, but it is then helping us to bring the cost down later in the month. So again, this is work in progress, but kind of interesting. The other data set that I mentioned is the HF radar. So this is a more challenging data set to fit because we're not assimilating any velocity constraints. And this is a coastal data, so we're away from this crossover region where we had more observations. The data that I'm using is the gridded product. So we have the zonal velocity and the meridional velocity observations separate. And I'm plotting again the RMS difference as a function of time. This is in meter per second. And so the forward model run will be the dashed line. The experiments that withhold data sets in blue, and then the state estimate in black. And so the observations are kind of along the coast, and there is one region where they overlap with the SWOT data. And so this is what I'm plotting in the bottom row here. So if I look just in where we have SWOT observations, that's where the state estimate can fit the velocity data. Whether we're assimilating just SWOT or SWOT plus Goose, we get similarly good improvement. It's not a massive improvement, but it is an improvement in this zonal velocity. And for reasons that I don't understand yet, we're not doing as well in the meridional velocity, but still there's a little improvement, maybe, arguably. So, and again, this is something I want to look more into, but it's a fun data set to try to compare to. And then I'm just going to show some examples of how the model is adjusting the controls to fit the data. So in the okay, this is temperature at 100 meters on May 1st, so at the very beginning of our simulation. So I mentioned that we use the Glory's initial conditions. So these are the adjustments to the Glory's initial conditions that are made by the model. So even though when we simulate only SWOT, we have so only sea surface height observations, but the information propagates to depth, right, all the way to at least 100-meter and deeper in the water column because of the dynamics in the model, right? So the constraints can propagate the information both in space and in time. We can see that the adjustments are mostly in the where we have data, but it does propagate. We have coastal signals there that might reflect wave propagations. The global ocean observing system adjustments have a different pattern, more spread out throughout the domain, and this is mostly just the superposition of the two controls. Not exactly, but pretty close. And then we also adjust the atmospheric states every day. So this is just showing zonal winds on May 15, but I could make a plot like that for each of the 7 atmospheric state constraints and for each of the 31 days of the assimilation. But just as an example, these are adjustments to wind speed in meter per second. And again, we have similar, um, mostly along the SWOT tracks. And then around these dots are the Argo profiles and the spray lines in gray, and then the total of the two. And yeah, I'm gonna leave it at that, and we'll be happy to discuss just in terms of um, what we're gonna do next. I want to repeat a similar 1 month assimilation for different times and see if we get consistent results. I'm ready to move on to assimilating the full SWOT data set now and not subsampling. See if that helps us resolve the small scales, which in the wave number spectra, we're not, we don't have as much energy as SWOT does at the small scales. So see if we can improve that. Eventually, doing a state estimate during the science orbit with a 21-day repeat cycle. Um, and I'm interested in comparing with other assimilation products. If people in this group want to do some comparisons, I think that would be very fun. And then one thing that I'm interested in separately is looking into biogeochemistry. So all these small scale are very important for vertical velocities, which bring in carbon and nutrients and has big implications for carbon and productivity. So we have a forward model run that has a biogeochemical model in it, and I'm plotting here the surface PCO2, and it already has some skill compared to mooring observation. So it would be super fun eventually to assimilate this biogeochemical data as well. But that is very much a future, and we don't have any funding to do that yet. I will stop here and looking forward to our discussion.
Thank you so much, Ariane. That was great.
Thank you.
Questions for Ariane? And we should really start with questions. Yeah, Greg, go ahead.
Thanks, Ariane. Really nice stuff. You had shown the plot of the normalized observation errors, the bar chart, with
Yes.
the different experiments with just the goose, just the SWOT. And a thing that strikes me here is assimilating just SWOT. the errors to the goose data are large. When assimilating goose, the errors to the SWOT data are large. It's kind of like the two data sets are in conflict with each other. They don't want to play together well. Uh,
Right.
and you had shown the plot of the corrections that were made from each data set or during in each experiment. It is very apparent. They cover very different areas, which I imagine leads to some of the conflict. They're each correcting different locations, so they don't have a chance to show they can affect one another. But in the HFR radar data, you had restricted the comparison to the SWOT paths, and I thought that might help here. Have you tried doing that when comparing these different data sets?
I have not. That's a very interesting point. We could focus on where data sets are co-located, and we might find qualitatively different results there. Um, yeah, I will
Ariane,
get in mind.
so I mean, I think we need to keep uh, distinguish the word conflict and independent. The cost doesn't go up when you omit it; it just doesn't go down much. So I think they're not in conflict. I think it's saying SWOT is adding new information and Goose is adding new information.
Yes, a much better description.
But we might see more of an improvement in, let's say, the goose or the state inside the SWOT path, then this is looking at the entire domain, right? So if I'm looking just at Argo, I could select only the Argo profiles that are within the SWOT area, and then might see more of an improvement from assimilating SWOT and fitting that Argo. So yeah, that's a good point. I could make another bar chart looking at that specifically.
Okay. I don't want to make too many bar charts for you, so
Oh, I like making them.
thanks a lot.
Thank you.
Spencer.
Hi. Yeah,
Hi.
it was a really nice talk. I guess I was thinking about, so can you repeat for us the atmospheric time resolution? And is it possible that one reason that the submesoscale isn't improving is that the time resolution of the atmospheric state is like fairly low? Yeah. So it's like
Yeah,
one
okay.
day. Do you
It's
think that's a factor?
okay, good question. First of all, the atmospheric state that I'm using is ERA5, which is an hourly product. However, the controls are a 1 day block. So yes, that is a limitation. So this is our way of creating smooth controls because we don't want to overfit, right? So this is why we're applying a spatial smoothing scale, and then we have this kind of temporal smoothing. Um, so this might be something that we want to look into tweaking, and Matt and Bruce can and Ganesh can advise me here because don't have as much experience with how much flexibility do we have there? But maybe if we changed um, the time scale over which we adjust the control, we can get more ability to fit. Matt, do you want to chime in on that?
I do. I'd like to throw the question back at Spencer and say, if we were going to deterministically control the submesoscale so we get them exactly as the real ocean gets them, do you think we could do that with the atmospheric state?
I mean, it seems like the most relevant field. But yes, I also am not. I don't even know whether this is possible to fit the submesoscale well. It's but you can't know unless you try to do it, I guess.
Yeah,
um,
I think that it's a research question how you control the submesoscale. It may be only with initial conditions, and then if that's the case, we would have to shorten the window. But I think it really depends on which direction the energy is going and if it's coming, if the maybe. But yeah, maybe we can talk more about how to control the submesoscale with you later.
And this
yeah, I think I'm also like I'm motivated right by to ask this question because I would like to figure out what is wrong with LLC 4320 is and I think this research is a very helpful direction to figure out like where are we not statistically doing well and why. So
And I was just going to mention the shortening the assimilation window is something else that I'm trying. Right now, I'm starting a new assimilation for a different time period, and I'm trying to do a 7 day as well as a 15 day assimilation, which was kind of motivated by when I'm not sampling, I just have so much data that I couldn't do 31 days, memory issues. So I'm starting to shorten it, and I don't have results yet from that, but we might be able to get more, or at least fit the data better over a shorter period like that. So I will keep you updated on these experiments.
Patrick.
Yeah, hi, Ariane. Great work. I wanted the uh, on the building on this previous question, but asking even simpler one. Did you actually look at the adjustments to the atmospheric state, look at the pattern? So what I'm wondering is what is the magnitude and the spatial pattern of these fields, just to get a sense of how large they are and how they, yeah, just how they look.
Yeah. So, yes, I've looked at some, but I need to dig in more into this. So, one of the questions that we were talking about last week is how do these fields look on day one as opposed to on day 15? So, I need to, based on this result here, where I'm seeing something odd is happening at the beginning. So I want to dig in more and figure out what are the adjustments here at the beginning of the simulation. And is it the winds? Is it the the heat fluxes? So I need to do more looking into these patterns. But yeah, sorry, did you have
Actually,
some
sorry, no, actually, I
suggestion of something
realized I missed.
specific?
No, actually, I missed. For some reason I missed that these are the you showed them, right? So, and I had completely missed that. No, that's great. I
And
mean,
then
it's
we have initial
and
conditions. So
yeah. So this initial condition. No, I think I agree with you. Would be having a sort of a time series, maybe. I mean, just for yourself, um, get an animation of how these adjustments evolve over time, whether they're
yeah,
growing, but they don't seem like they're growing over time. But that could be useful. But I think as long as you're confident or comfortable with the magnitude, especially that they are not, yeah, that they are sort of in line with what you might expect from correction to the atmospheric state, that's great.
right. Yeah, no, they seem
Mhm. Yeah.
plausible so
Mhm.
far. Yeah.
Yeah.
So Greg Jacobs has a comment in the chat. He says that they have several experiments of 3D bar that could be provided um, for the Scripps group or anyone else who would like to compare. The analysis they've done is not as complete, but they know the addition of SWOT advances the skill compared to Cal-Val moorings.
Yeah, that would be great.
And maybe that lays the groundwork for thinking about some collaborative efforts that might go into comparison. Patrick, you have your hand up.
Yeah, so if you do this type of comparison, I think it would be really interesting to especially compare the vertical velocity, right? Because that's a big question about how does vertical velocity behave in, which is not assimilated, but it's an important quantity, especially for biogeochemistry, vertical
Mhm.
transport, and how they compare in 3D versus 4D VAR.
Great. I made a note of that. Thank you. Will do.
Are there other questions? If not, I have some questions for the group as a whole. We had spoken to Greg a little earlier about this work, and I think that Greg posed a question, is it possible to get to scales smaller than 70 kilometers? And I guess the question is anybody getting successful assimilation to get to that sub-mesoscales at the moment? Does anybody have a magic bullet for this?
I think a historical perspective may help in that,
Mhm.
Ariane's showing that it's working really well at these scales.
Mhm.
And I think 10 years ago, we would have said, this is kind of mind blowing. And now it seems more acceptable because we have the mesoscale more constrained and we get products like Glories to initialize from. And so I think as the mesoscale becomes constrained, we start pushing towards the smallest of the mesoscale, like the 70 kilometers. I think it's very much an iterative process throughout each scale. And once we have products that are doing great at 70 kilometers, I think it won't be a challenge to push it down to 10 kilometers or 7 kilometers. I think we'll get the
Mhm.
next order of magnitude because we'll start close, because we'll have maybe shorter windows because the large scale, longer time scales and space scales are already constrained by other products or our own nested products. So I think it's just a question of one step at a time.
That seems like a good perspective. I guess the counter perspective would be the pessimistic one that Matt is fortunately not voicing, that some mesoscales are fundamentally nonlinear and are going to be much, much more challenging. Greg.
Um, I'll throw in another pessimistic opinion. It seems a lot of people are having difficulty estimating velocities, maybe from SWOT. Maybe, Sarah, that's a good thing for you. Going down to those smaller scales. And of course, the 4D VAR, it's not necessary to tell it what the velocities are related to the sea surface height. It will estimate the relations based on its dynamics, but is it an indication that given just the sea surface height, people are having trouble extracting velocity at those smaller scales, and there's something we don't necessarily are taking into account or something we don't know. And so I think there's a bump there in the road we don't understand yet.
Yeah, I think the adventures lie ahead. Ryan.
Yeah, I would just like to kind of agree with what Greg is mentioning, right? Is there are studies coming out now that looks at what the small scales of SWOT is actually correlated to, and it seems like at least till 30 kilometers or even larger, ready for pessimistic, that is correlated to wave properties instead of so perhaps we're missing something that the SWOT observation shouldn't correct, shouldn't be just SSH, might be something else. Um,
So not that SWOT is wrong, but that it's measuring a different dynamical process than we were
right.
expecting.
Or it's actually just noise, right?
Mm,
Hard to tell.
depends what you call noise, maybe.
Right. Yeah. But I mean, the kind of theory of SWOT noise should correlate it with kind of match what we see in the small
Mhm.
scales of SWOT observations.
Well, I have one more question for the group because Ariane showed this, um, and this was discussed earlier, this interplay or competition between initial conditions and atmospheric forcing, and the sense that the atmosphere is maybe way more important for the duration of the run than the initial conditions. And again, I'm curious if anybody else has encountered anything that has a flavor like this? And is this telling us that what really matters is atmospheric forcing? And does that mean that we need better atmospheric forcing conditions or better, more willingness to adjust them? So I'm curious what people have to say on this. Patrick.
I don't want to be pessimistic, but I remember the very first Echo product had, of course, coarse resolution, 2-degree ocean model, and, sort of old reanalysis product. And if you saw the atmospheric adjustments or the air sea fluxes, it was the fluxes at the time, was basically over the Gulf Stream, there were these massive wind dipoles and heat flux dipoles which helped to basically put the Gulf Stream kind of back into the somewhat of a right place. And so what this means is that you have a knob to control the system by doing by tweaking the knob to get the observation right of the interior, but at the expense of putting, a seemingly wrong pattern into the RC fluxes, right? So momentum and heat flux. And so the question is, and the worry is, the more, I mean, it can, so these adjustments, the dominance in the atmospheric state, and because you at the daily scale, you can change those, right? So you can get especially
Mhm.
surface properties right. Are those knobs again correcting for correct observations at the expense of potentially wrong atmospheric states? So that's also why I asked the question. Let's say I'm hoping that's not the case, or it may even be the case, and it may even be okay. But it's just something
Mhm.
to be cognizant of to exactly understand what they do. And again, I think it can be okay because you want to have the dynamics right. But it's just something to be maybe cognizant of that there are controls that allow you to maybe to correct for model error by just changing them. But maybe Matt has a different perspective here. Yeah.
Well, I'll be optimistic in saying that this is why we held data independent, because if we were getting the right answer for the wrong reason to SWOT, probably wouldn't fit the goose or the moorings. So I think it is fixing uh, the atmospheric state to what the ocean wants. I mean, I agree that there's errors that are being compensated in say the bulk formula, and maybe the mixing's wrong, too weak, so it puts too much wind or something, and there's actually it's not more consistent with the atmosphere. But it is fixing the fluxes. I think it's doing the right thing. Um, but to get at Sarah's question, and I know I should move on. But to get at Sarah's question, I think the atmosphere is, and this is also Spencer's comment, the atmosphere is able to help us fix the scales in the ocean down to say 70 kilometers. As you get below that, um, what are the drivers? And this is I think, a research topic.
Greg.
Yeah, I like Patrick's point. And the corrections made to the atmospheric forcing are not necessarily to be expected to be the errors in the atmosphere, but there is growth in the errors of the state over time, just because small errors in the initial condition are going to grow in time. And people argue for weak constraint 4D-var, not necessarily because there's errors in the dynamical equations or the finite difference equations, but there's a need to make those small corrections to keep the growth of errors down. And sometimes you just put errors in a place that's convenient to be able to get the forcing over time. The atmosphere may just be a convenient place to try to get the corrections of errors injected into the system.
Yep.
That seems like a useful framing.
And Patrick, I do recall those early echo results over the Kuroshio and Gulf Stream with the very interesting wind patterns.
Yeah, and again, this is kind of what Spencer's saying is we need to figure out where the model errors are, put the controls in those locations, and not blame them all in the atmosphere. Because you're right, these are not all errors in the atmosphere. These are compensating some ocean parameterization errors.
It gives us lots of space to watch. And maybe some places where there's room for a continued community discussion. Try and converge more rapidly on the useful strategies.
I still think it's the right thing to do. I mean, yeah, I mean, and I think maybe one learns even from those adjustments and can basically, what do they tell us about potential? Are they real or are they model error? So I'm not questioning the approach. I'm just cautioning sort of the interpretation. Yeah.
Any other thoughts for today? Any updates anybody wants to share? If not, we will continue this working group discussion next month with Shoshi Reich from UT Austin, who's going to talk about some of the work she's doing. And the schedule is laid out through June, so there's lots more to come.
Thank you for organizing, Sarah.
And thanks everyone for a really great discussion, and thank you, Ariane, for a great presentation to get us started.
Thank you.
Yeah.
This is
Great job.
fantastic. Thanks,
Yeah.
thanks, Ariane.
Well, thank you very much for the questions and feedback, and I look forward to keeping in touch.
Bye.
Bye.
Thank you. Bye.